Hello there, and welcome to Deep Sleep Seas. I'm so glad you found your way here tonight. Perhaps you've had a long day, or maybe you're the kind of person who finds comfort in the gentle mysteries of the ocean rather than counting sheep. Either way, tonight's voyage is for you. You have nothing to do but rest, let your mind settle, your breathing slow, and your body grow light as if the water itself is cradling you. Because tonight we aren't simply exploring the ocean's surface. We're descending into one of its most peculiar and mesmerizing phenomena, something that defies expectation and challenges what we think we know about the laws of nature. We're discovering undersea sandfalls, the ocean's slow cascading sands. Picture, if you will, a waterfall. You know the image well. Water tumbling over a cliff's edge, white foam catching the light. The roar of liquid meeting liquid below, mist rising like breath in cold air. We understand waterfalls. They make sense. Water falls through air because water is heavier than air. Gravity pulls it down, and we stand at the bottom, feeling the spray on our faces, marveling at the power and beauty of it all. But what happens when the medium changes? What happens when you're already underwater, surrounded by water in every direction, and yet something still falls? Not water through air, but sand through water, earth through liquid. The ocean floor itself, tumbling in slow motion over underwater cliffs, creating rivers of sediment that pour like honey through the depths. These are sandfalls, and they exist in places so remote, so deep, and so quiet that most people will never witness them. But they are there, moving constantly, reshaping the ocean floor grain by grain, carrying stories from the shallows to the abyss. Tonight we'll travel to volcanic islands where sandfalls create optical illusions so convincing they've been photographed from helicopters and mistaken for magic. We'll visit underwater canyons where ancient earthquakes triggered avalanches of sediment that raced across hundreds of miles of seafloor, snapping telecommunications cables like threads. We'll descend to the Denmark Strait between Iceland and Greenland, where the world's tallest waterfall flows entirely beneath the surface, invisible to satellites, undetectable to ships passing overhead, yet moving more water than every river on Earth combined. We'll witness how sand behaves when it's suspended in water, how it moves differently than it does on land, and how these slow cascades have been shaping our planet for millions of years. Some of what you hear tonight may surprise you, but all of it is real. The ocean holds wonders that seem impossible until you understand the physics, the geology, the quiet mathematics of density and gravity working together in darkness. Before we begin, if you find these stories soothing, consider subscribing so you don't miss the next journey into the deep. And if you're still awake enough, let me know where in the world you're listening from. I read every comment and love knowing that we're all connected by the same ocean, the same curiosity, the same need for peace at the end of the day. Now, let's begin. The water is calm, the light is fading, and the sand is already beginning to fall. The first thing you need to understand about sandfalls is that they shouldn't exist. At least, not in the way we typically think about falling. When you drop a grain of sand through air, it falls quickly, almost instantly. Gravity acts on it with little resistance. The air is so much lighter than the sand that the grain barely notices it's there. It accelerates downward at nearly 10 meters per second squared, slowed only slightly by air resistance. But underwater, everything changes. The water itself is dense, nearly 1,000 times denser than air. When a grain of sand tries to fall through water, it encounters resistance at every fraction of a millimeter. The water molecules push back, creating drag, slowing the descent dramatically. A single grain of sand falling through still water might take minutes to travel what would have taken seconds in air. It doesn't plummet. It drifts, it wobbles, it spirals in tiny helixes as the currents catch it. And yet, despite this resistance, despite the water pushing against it, the sand still falls. Because sand is denser than water. Even with all that resistance, gravity wins. Slowly, gently, inevitably, the sand sinks. This is the fundamental principle behind undersea sandfalls. They exist because of density differences. Sand particles made primarily of quartz or calcium carbonate or crushed shells or volcanic minerals are heavier than the seawater surrounding them. When enough sand accumulates in one place, when it's pushed to the edge of an underwater cliff or swept along by currents until it reaches a drop-off, it begins to cascade. Not with the violence of a terrestrial waterfall, but with a slow, almost dreamlike quality. Imagine watching honey pour from a jar, the way it moves in thick ribbons, folding over itself, golden and translucent. That's closer to how sand falls underwater. It maintains some cohesion, grains clump together. They form clouds, and as they descend they can pick up more sediment from the seafloor, growing larger, moving faster, creating what scientists call turbidity currents, underwater rivers of sand and silt that flow like liquid earth through the deep. The speed at which sand falls depends on many factors. The size of the grains matters enormously. Fine silt, particles smaller than 1/10 of a millimeter, can take hours to settle through a few hundred meters of water. They're so light, so small, that even the tiniest currents can keep them suspended, drifting sideways as much as downward, creating hazy clouds that obscure visibility for divers and submersibles alike. Medium sand, the kind you might find on a beach, grains about 1/2 a millimeter across, falls faster but still slowly compared to air. In perfectly still water, such a grain might sink at a rate of a few centimeters per second, not fast but steady. Coarse sand and gravel, particles larger than 2 millimeters, fall with more authority. They can reach speeds of 10 or 15 centimeters per second, fast enough that you could watch them descend if you were suspended in the water column beside them. But even this is gentle compared to the rush of a river or the crash of a terrestrial waterfall. Everything underwater moves as if through a dream, slowed by the viscosity of the medium, the eternal embrace of the sea. Temperature affects falling speed too. Cold water is denser than warm water, which means it offers more resistance. A grain of sand falling through the icy waters of the Arctic Ocean will descend more slowly than the same grain falling through tropical shallows. Salinity plays a role as well. Saltier water is denser, which increases drag. The ocean is not uniform. It's layered, stratified, a sandwich of temperatures and salinities that change with depth. As sand falls through these layers, its speed changes. It might move quickly through warm surface water, then slow dramatically when it hits a cold thermocline 100 meters down, then speed up again as it enters the abyss where pressure compresses the water slightly and temperature stabilizes. The journey of a single grain of sand from the surface to the deep ocean floor is not a straight line. It's a zigzag, a dance with currents, a negotiation with physics that can take days or even weeks for the finest particles. But undersea sandfalls are rarely about individual grains. They're about mass movement. They're about millions, billions, trillions of grains moving together, creating a collective force that behaves differently than any single particle. When sand moves in bulk, especially when it's driven by currents or triggered by some disturbance, it doesn't fall one grain at a time. It flows. It cascades. It forms what looks eerily like a waterfall made of earth, a river of solid matter pouring through liquid, defying the intuition that tells us things should only fall through things lighter than themselves. And in a few rare spectacular locations on Earth, this phenomenon becomes visible, becomes dramatic, becomes something you can witness with your own eyes or from a helicopter hovering above crystal clear tropical waters. It becomes art rendered in sediment and light. Let's travel now to one of these places. Close your eyes and imagine yourself flying. You're in a small helicopter, doors open, wind rushing past, the sound of rotors thumping rhythmically above you. Below, the Indian Ocean spreads out in every direction, a vast expanse of blue that shifts and changes with the depth of the water beneath. You're approaching the island of Mauritius, a volcanic island that rose from the ocean floor millions of years ago, part of a chain of islands sitting on a submarine plateau far off the eastern coast of Africa. From this height, Mauritius looks like an emerald jewel set in turquoise silk. The island is green with vegetation, ringed by white beaches and coral reefs. But as your helicopter curves around toward the southwestern coast, toward a peninsula called Le Morne, you see something that makes your breath catch, something impossible. Something that looks exactly like a waterfall plunging into the depths, except you're looking at it from above, through hundreds of meters of clear ocean water. The phenomenon is stunning. From your aerial vantage point, it appears as if the ocean itself is draining away, pouring over an underwater cliff into some deeper abyss. The water near the coast is pale, almost white, with suspended sand and the reflection of shallow reefs. But as you look outward, the color deepens through shades of turquoise and azure, and finally to the profound cobalt of deep ocean. And right at the transition, right where the shallow shelf ends and the deep begins, there's a distinct vertical line, a boundary that looks for all the world like the edge of Niagara Falls or Victoria Falls. The water seems to be flowing over it, cascading downward, creating swirls and eddies visible from the air. Your brain tells you this is a waterfall, Your eyes insist on it. But your knowledge of physics whispers something else. Water doesn't fall through water. Not like this. Not unless something else is happening. What you're seeing is the Mauritius underwater waterfall, one of the most photographed natural phenomena in the world, and one of the most misunderstood, because it's not a waterfall at all. It's a sandfall. Mauritius sits on the Mascarene Plateau, a massive underwater shelf that stretches across this part of the Indian Ocean. Near the island, the plateau is shallow, no more than 150 meters below sea level, but at its edges, particularly off the southwestern coast near Le Morne Peninsula, this plateau ends abruptly. The seafloor doesn't slope gradually into deeper water. It drops. Cliffs plunge from the shallow shelf down to depths of 4,000 meters or more. It's a submarine cliff face, a wall of rock and sediment that falls away into darkness, and along this edge, something remarkable happens. The ocean currents that flow around Mauritius, driven by trade winds and the rotation of the Earth, sweep along the shallow shelf. They carry sediment with them. Sand eroded from the volcanic rocks of the island, shells pulverized by waves, tiny fragments of coral broken off by storms. All of this material is light enough to be suspended in the moving water, carried along like dust in wind. But when these currents reach the edge of the plateau, when they encounter the drop-off, the physics changes. The water keeps flowing, pushed by wind and tides and the great gyres of the Indian Ocean. But the sand can't keep up. The currents might carry water over the edge and into the deeper basin beyond, but the sediment within that water is too heavy. It begins to sink. As the current sweeps it over the cliff, gravity takes over. The sand falls, not all at once, not in a coherent sheet, but grain by grain, cloud by cloud, creating a continuous rain of sediment that tumbles down the submarine cliff face. And from above, from a helicopter, or even from satellite imagery, this falling sand creates an optical illusion. The suspended sediment forms patterns, shapes, swirls that look exactly like flowing water. The lighter colors of the sand-laden water contrast sharply with the darker, clearer, deep water below. The movement of the sand as it cascades downward creates streaks and curves that mimic the appearance of turbulent water going over a falls. It looks like the ocean is draining away. It looks like Poseidon himself has pulled a plug at the bottom of the sea, and the whole ocean is spiraling down into some cosmic bathtub. But it's sand, just sand, falling slowly, constantly, beautifully, creating one of the most convincing optical illusions nature has ever produced. The Mauritius sandfall has become famous in recent years, shared millions of times on social media, featured in travel magazines and documentaries. Helicopter tours specifically advertise flights over this phenomenon, circling the area so passengers can photograph the spectacle from every angle, and it is spectacular. The way the colors shift from pale jade near the shore to deepest navy in the abyss creates a sense of depth and movement that's almost dizzying. The patterns in the sand, shaped by currents, and the contours of the seafloor form what look like fingers of water reaching into darkness. Some days when the currents are particularly strong, when storms have churned up extra sediment, the effect is even more dramatic. The sandfall appears wider, more vigorous, as if the volume of water pouring over an invisible precipice has increased. Other days, in calm conditions, the patterns are subtler, more delicate, requiring a trained eye to pick out the cascade from the surrounding ocean. But you can't see the sandfall from sea level. That's one of its peculiar qualities. If you're in a boat at the surface, sailing right over this area, you won't notice anything unusual. The water looks like water. There's no sound, no spray, no obvious indication that beneath you, sand is falling 4,000 meters to the ocean floor. Even divers who explore the reef around Le Morne Peninsula rarely encounter the sandfall directly. The phenomenon occurs at depths and distances from shore that require specialized equipment and planning. The currents that drive it can be strong, making diving dangerous, and underwater, surrounded by the same water that surrounds the falling sand, the optical illusion disappears. You might see clouds of suspended sediment drifting past, but you wouldn't perceive them as falling unless you specifically looked for it. The sandfall exists primarily from above, a trick of perspective and contrast, nature's own sleight of hand performed with millions of tons of crushed volcanic rock and ancient coral. Mauritius is not alone in hosting such phenomena. Across the ocean on the other side of the world, there's another famous sandfall, though this one is far less accessible, far more mysterious. We must travel now to Cabo San Lucas, the very tip of the Baja California Peninsula in Mexico, where the warm waters of the Sea of Cortez meet the cold, deep Pacific Ocean. This is a place where tectonic forces have shaped the seafloor in dramatic ways. The Baja Peninsula is slowly tearing away from mainland Mexico, pulled by the spreading of the East Pacific Rise, creating the Gulf of California, which locals call the Sea of Cortez. This geological violence, stretched across millions of years, has fractured the ocean floor, creating trenches, ridges, and underwater walls that plunge from shallow bays into abyssal depths within just a few hundred meters of shore. Jacques Cousteau, the legendary ocean explorer, famously called the Sea of Cortez the world's aquarium because of its incredible marine biodiversity. The waters here are extraordinarily rich. Nutrients well up from the deep, feeding plankton, which feed fish, which feed dolphins and whales and sea lions. The biodiversity is staggering. But beneath the teeming life, beneath the schools of fish and forests of kelp, there are places where the ocean floor simply drops away. And in one particular location, divers have discovered something extraordinary: a sandfall. But unlike the optical illusion at Mauritius, this one is real. This one you can dive to, swim through, watch as it happens around you. At depths of more than 30 meters, where sunlight begins to fade and pressure makes every breath from your regulator feel precious, there are walls. Steep underwater cliffs formed by the tectonic forces that are slowly pulling this peninsula apart. These walls are encrusted with life. Black corals, rare and ancient, cling to the rock, their polyps filtering the nutrient-rich water for microscopic prey. Sponges in brilliant colors, yellows and oranges and deep purples, cover every available surface. Fish dart in and out of crevices, and if you're lucky, you might see eels or octopuses, or even a passing manta ray. But the main attraction, the reason advanced divers come to this particular spot, is the sand. Because over these walls, constantly, endlessly, sand is falling. The Sea of Cortez is surrounded by deserts. The Sonoran Desert and the Baja Desert stretch for thousands of square kilometers, and when winds blow, they carry dust and sand out over the water. Storms wash sediment down from the mountains. The grinding action of waves on beaches pulverizes shells and rocks into sand. All of this material accumulates on the shallow shelves near shore, and when underwater currents, driven by tides and wind and the mixing of Pacific and Sea of Cortez waters, push this sand to the edge of the underwater cliffs, it cascades down. It falls in streams, in rivers, in clouds that look like smoke drifting through the water. Divers describe it as surreal, watching sand pour over the edge above them, descending in slow motion past the encrusted walls, settling on ledges, and then sliding off again, continuing its journey to the depths below. Some of the grains fall individually, spiraling and tumbling. Others clump together, maintaining some cohesion as they sink. The water becomes hazy with suspended particles, reducing visibility but creating an ethereal atmosphere, like diving through fog, except the fog is made of earth. The black corals that thrive on these walls have adapted to this constant rain of sediment. In most ocean environments, corals need clear water. Sediment settling on their polyps can smother them, blocking their ability to feed and breathe. But black corals are tougher, more resilient. They can shed sediment, using tiny hair-like structures to move particles off their surfaces. They've evolved in environments where sedimentation is a constant challenge, and they've found ways to cope. Their presence here, in such abundance, tells you that this sandfall is not a recent phenomenon. It's been happening for a long time, perhaps for thousands of years, perhaps even longer, as long as there have been currents, as long as there's been sand and gravity and underwater cliffs. This process has been ongoing. The ocean floor beneath these falls is deep, much deeper than recreational divers can reach. The sand accumulates there, building up over centuries and millennia, forming deposits that compress over time into sedimentary rock. If you could core through those deposits, you would find layers, each one representing a different period of time, a different storm season, a different era of geological history. The sandfall is writing a book in stone, one grain at a time, recording the story of wind and water and the slow erosion of continents. Diving the Cabo San Lucas sandfall requires experience, proper equipment, and respect for the ocean's power. The currents can be unpredictable. The depth pushes the limits of recreational diving, and going deeper requires technical training and more complex gear. But for those who make the journey, who descend through the dimming light to witness this phenomenon firsthand, it's transformative. There's something profound about watching Earth fall through water, about seeing the process that connects mountains to ocean floor, about recognizing that the ocean is not static, not unchanging, but constantly in motion, constantly reshaping itself according to laws written in physics and geometry and time. But sandfalls are not always gentle. They're not always slow cascades you can hover beside and photograph. Sometimes, under the right circumstances, sandfalls become catastrophic. They become underwater avalanches that race across the ocean floor at speeds that would terrify any terrestrial skier. They become turbidity currents, and they're among the most powerful forces in the ocean, capable of reshaping entire continental margins, of carving canyons deeper than the Grand Canyon, of transporting more sediment in a single event than all the rivers on Earth carry in a year. To understand turbidity currents, we need to talk about density and momentum, and the concept of positive feedback loops in nature. Imagine a pile of sand at the top of a slope. On land, if something disturbs that pile, maybe an earthquake or heavy rain, the sand might start to slide. As it slides, it picks up more sand, growing larger, moving faster. This is a landslide, and it's driven by gravity. The sand is denser than air, so it flows downhill, and as it flows, it can accelerate, becoming more destructive. Underwater, the same principle applies, but with an important difference. The sand is not moving through air, it's moving through water, and as it moves, it mixes with the water, creating a slurry, a mixture of sediment and seawater that is denser than the surrounding clear water. This slurry flows downhill along the ocean floor, not because the sand alone is heavy, but because the entire mixture is heavy. At first, a turbidity current might start small. Maybe a storm has deposited a large amount of sediment at the head of a submarine canyon, one of those deep underwater valleys that cut into continental shelves. The sediment sits there, piled up, unstable. Then something triggers it. An earthquake shakes the seafloor. A particularly large wave disturbs the pile from above, or perhaps the pile simply grows too large and collapses under its own weight. Whatever the trigger, the sediment starts to move. It slides down the canyon, picking up water as it goes, mixing into a turbulent cloud. And here's where it gets interesting. As the turbidity current flows downhill, it encounters more sediment on the canyon floor. The turbulence within the current, the churning and mixing, picks up this sediment, suspending it in the water. The current grows denser. Denser water flows faster downhill. Faster flow creates more turbulence. More turbulence picks up more sediment. The current grows even denser, even faster. It's a runaway process, a positive feedback loop that can turn a small slump of sediment into a roaring underwater river of sand and silt that travels at speeds of 20, 30, even 50 kilometers per hour or more. These turbidity currents are invisible from the surface. You could sail a ship directly over one and never know it was there. But beneath the hull, on the ocean floor, an avalanche is racing past, carrying billions of tons of sediment from the continental shelf out to the deep ocean basins. And if there happens to be a submarine telecommunications cable in the path of that current, the cable doesn't stand a chance. The current can bury it under meters of sediment, crushing it, or the turbulence can lift it off the seafloor and then drop it, breaking it, or the sheer force of the flow can pull it out of position, snapping it like string. This is not theoretical. This has happened multiple times throughout history, and each time, it's caused massive disruptions to global communications. The most famous example occurred on November 18, 1929, off the coast of Newfoundland in Canada. On that day, a magnitude 7.2 earthquake struck the Grand Banks, a shallow area of the North Atlantic Ocean southeast of Newfoundland. The earthquake itself was powerful enough to be felt on land, but the real impact came from what it triggered underwater. The shaking destabilized massive amounts of sediment that had accumulated on the continental slope over thousands of years. This sediment, loosened by the earthquake, began to slide, and as it slid, it created a turbidity current of unprecedented scale. The immediate effect was a tsunami. The sudden movement of the seafloor displaced water, sending waves crashing into the Burin Peninsula on Newfoundland's south coast. 28 people died. Entire communities were devastated. Homes were swept away. But scientists at the time didn't fully understand what had happened underwater. They knew there had been an earthquake and a tsunami, but they didn't realize the full extent of the turbidity current until they examined the telecommunications cables that crossed the area. There were 12 submarine telegraph cables running across the Grand Banks connecting North America to Europe. These cables were essential for communication between the continents. When the earthquake hit, 6 of the cables broke immediately, presumably from the direct shaking or from the initial slumping of sediment. But the other 6 cables broke in sequence, one after another, over the course of 13 hours, at locations progressively farther from the epicenter of the earthquake. The breaks occurred along a line extending more than 600 kilometers from the continental slope out onto the abyssal plain, and the timing of each break told a story. Scientists calculated the speed of the turbidity current by measuring the time between the earthquake and when each cable broke, and the distance each cable was from the epicenter. The current traveled fastest near the beginning of its journey, reaching speeds of about 100 kilometers per hour as it roared down the steep continental slope. As the seafloor leveled out onto the abyssal plain, the current slowed but still maintained incredible momentum, flowing for hours across the flat ocean floor before finally dissipating. This single event deposited a layer of sediment across an area of over 100,000 square kilometers, some locations receiving deposits more than a meter thick. It was, by any measure, catastrophic, and it proved beyond doubt that turbidity currents were real, powerful, and capable of traveling enormous distances. Before the Grand Banks event, turbidity currents were theoretical. Scientists had proposed them as a mechanism to explain certain features of the deep ocean floor, but there was no direct evidence. The cable breaks provided that evidence. They gave scientists precise timing, precise locations, precise proof that these underwater avalanches were not just possible, but common throughout geological history. Since then, we've recorded other turbidity current events. In January of 2020, a turbidity current flowed from near the mouth of the Congo River in Africa, traveling more than 1,000 kilometers across the ocean floor and breaking multiple telecommunications cables as it went. The current lasted for more than 2 days, and the cable breaks disrupted internet service across multiple countries in West Africa, highlighting how dependent modern civilization has become on undersea infrastructure. These cables, thin strands of glass and metal lying on the ocean floor, carry more than 99% of all international data traffic. Every email, every video stream, every financial transaction between continents flows through these cables, and they're vulnerable. Vulnerable to fishing trawlers that snag them, vulnerable to ships that drag anchors across them, and vulnerable to turbidity currents that strike without warning, burying or breaking them in remote locations where repairs take weeks or months to complete. Studying turbidity currents is extremely difficult because they're so unpredictable and occur in places that are hard to monitor. Scientists have placed instruments on the seafloor in submarine canyons, hoping to catch a turbidity current in action, to measure its speed and sediment concentration directly, and in a few cases they've succeeded. Instruments in Monterey Canyon off the coast of California have recorded multiple turbidity currents triggered by storms that flush sediment from nearby rivers out onto the continental shelf and into the canyon head. These events are relatively small compared to something like the Grand Banks current, but they've provided invaluable data about how turbidity currents initiate, how they evolve as they flow, and how they deposit sediment. One of the surprising findings is that many turbidity currents are not triggered by catastrophic events like earthquakes. They can be triggered by much smaller disturbances. A large storm dumping rain onto a river basin, causing the river to carry more sediment than usual. This sediment flows into the ocean and settles at the head of a submarine canyon. Over time, it accumulates. And when the pile gets large enough, when the slope gets steep enough, it can fail on its own, collapsing and initiating a turbidity current. In some canyons, this happens multiple times per year, small events that go unnoticed except by the instruments patiently recording data in the darkness. But the largest turbidity currents, the ones that create the most dramatic changes to the seafloor, are triggered by major geological events. Earthquakes that shake loose enormous volumes of sediment, volcanic eruptions on islands that dump millions of tons of ash into the ocean, massive submarine landslides where entire sections of the continental slope collapse. These events are rare, thankfully, but when they occur, they can reshape the ocean floor on scales that are hard to comprehend. The sediment from a single large turbidity current can travel over 1,000 kilometers from its source, depositing layers that remain visible in the geological record millions of years later. Cores drilled from the deep ocean floor often show alternating layers of fine mud and coarser sand. The mud represents normal sedimentation, the slow rain of particles settling from the water column, accumulating at a rate of a few millimeters per 1,000 years. But the sand layers represent turbidity currents, single events that deposited centimeters or even meters of material in just hours or days. By analyzing these layers, by dating them and tracing them back to their sources, geologists can reconstruct a history of catastrophic events, mapping out where and when the largest turbidity currents have occurred over millions of years. Some of the most spectacular features on the ocean floor are created entirely by turbidity currents. Submarine fans, massive aprons of sediment that spread out at the mouths of submarine canyons, are built by countless turbidity events stacking layer upon layer over geological time. The Bengal fan, off the coast of India and Bangladesh, is fed by sediment from the Ganges and Brahmaputra rivers. It's the largest submarine fan in the world, covering an area larger than the Indian subcontinent itself, extending over 3,000 kilometers into the Bay of Bengal and the Indian Ocean beyond. All of that sediment was transported from the Himalayas, carried by rivers to the sea, and then swept into the deep by turbidity currents flowing through submarine canyons. The fan is more than 16 kilometers thick in some places, representing millions of years of accumulation, each layer a record of erosion and transport and deposition. To stand at the mouth of the Ganges, to watch the muddy water flowing into the Bay of Bengal, is to witness the beginning of a process that will continue for thousands of kilometers and thousands of meters below the surface. Some of the sediment will settle near the delta, but much of it will be caught by currents, swept along the shelf, and eventually channeled into canyons where it will begin its journey into the deep. And when it arrives, perhaps years or decades later, it will add another infinitesimally thin layer to a fan that has been growing since the Himalayas first began to rise. The underwater world is full of these hidden connections, these processes that link continents to ocean basins, mountains to abyssal plains. Sandfalls and turbidity currents are the arteries through which the ocean circulates solid matter, redistributing the products of erosion, building new structures in the deep while tearing down old ones. And nowhere is this more dramatic, more essential to the planet's functioning than in the Denmark Strait, where the world's largest waterfall flows entirely beneath the waves, unseen by human eyes, but felt by every ocean current, every weather system, every ecosystem that depends on the circulation of the sea. Let's descend now into the cold waters between Iceland and Greenland, to a place where two seas meet and where water itself, not sand, cascades over an underwater cliff in a flow so immense it dwarfs every river and waterfall on land combined. The Denmark Strait is a narrow passage, about 600 kilometers wide, separating Iceland from Greenland. On the surface, it's a forbidding place. Cold winds blow down from the Arctic. Icebergs carve from Greenland's glaciers and drift southward through the strait, some of them the size of buildings, grinding and groaning as waves buffet them. The water is steel gray, whipped into whitecaps by nearly constant winds. Ships that transit the strait must be prepared for rough seas and near freezing temperatures. It's not a place where you linger, but beneath the surface, hidden from view, the Denmark Strait hosts one of the most important oceanographic features on the planet, a waterfall, not of sand, but of water. Cold, dense water cascading over an underwater ridge and plunging thousands of meters into the depths. This waterfall is not visible. You cannot see it from a ship. You cannot photograph it from a helicopter. Satellites cannot detect it directly, but it's there, flowing constantly, year after year, century after century, moving more water than the Amazon, the Nile, the Mississippi, the Yangtze, and every other river on Earth combined. To understand how a waterfall can exist underwater, you need to understand that water is not all the same. Seawater varies in temperature and salinity, and these variations affect its density. Cold water is denser than warm water. Salty water is denser than fresh water. When you combine both, very cold and very salty water, you get water that is significantly denser than warmer, less salty water nearby. And dense water sinks. It flows downhill along the ocean floor, seeking the lowest point, just as sand does, just as any heavy fluid does when placed in a lighter medium. In the Arctic and North Atlantic, the waters of the Nordic seas, which include the Greenland Sea, the Norwegian Sea, and the Iceland Sea, are extremely cold. In winter, surface waters cool to near freezing, When seawater freezes, it forms ice that is almost pure water, leaving the salt behind in the remaining liquid. This process, called brine rejection, makes the unfrozen water even saltier and thus even denser. This cold, salty water sinks to the bottom of the Nordic seas, accumulating in basins and slowly moving southward, seeking an outlet. The Denmark Strait provides that outlet. The strait sits atop a submarine ridge, an elevated section of the ocean floor that separates the deep Nordic seas from the deep Atlantic Ocean to the south. The ridge is about 600 meters below the surface at its shallowest point. To the north, the Nordic seas are around 1,400 meters deep. To the south, the Erminger Sea, part of the North Atlantic, drops to over 3,000 meters. The ridge acts like a dam holding back the cold, dense water of the Nordic seas. But the dam is not complete. There are passages, channels where the ridge is lower, where the cold water can overflow, and when it does, it cascades down the southern side of the ridge in what has been measured as the world's largest waterfall by volume. The cataract itself is not a sheer drop. It's more of a steep slope, descending over a distance of about 500 to 600 kilometers. But the vertical drop is immense, approximately 3,500 meters from the top of the ridge to the bottom of the Erminger Basin. That's more than 3 times the height of Angel Falls in Venezuela, which is the tallest waterfall on land. The volume of water flowing over the Denmark Strait cataract is estimated at around 5 million cubic meters per second. To put that in perspective, the flow over Niagara Falls, one of the most powerful waterfalls on land, is about 2,500 cubic meters per second at peak flow. The Denmark Strait cataract carries 2,000 times more water. It's an almost incomprehensible amount, and yet from the surface you would never know it's there. Ships pass over the cataract regularly, traveling between Europe and North America, and the captains have no idea that beneath them, a river of cold water the size of multiple Amazons is pouring down an underwater mountain. The reason it's invisible is simple. The waterfall is not water falling through air, it's cold water falling through slightly warmer water. There's no surface disturbance, no white foam, no sound. The boundary between the cold, dense water and the warmer water above it is a thermocline, a gradient in temperature that can be measured with instruments but cannot be seen with the eye. If you were in a submarine descending through the Denmark Strait, you would pass through layers of water at different temperatures. You'd notice the temperature dropping on your instruments, but you wouldn't see a waterfall. The water would look the same in all directions, just slightly darker as you descended and light from the surface faded. But the effects of the cataract are far-reaching. The cold water that flows over the Denmark Strait doesn't just settle at the bottom of the Erminger Basin and stay there. It continues southward, hugging the ocean floor, forming part of what's called the North Atlantic Deep Water, one of the major currents in the global ocean conveyor belt. This conveyor belt, properly called the thermohaline circulation, is driven by differences in temperature and salinity. Warm surface water from the tropics flows northward, driven by winds and the rotation of the Earth. As it reaches the high latitudes, it cools, releases its heat to the atmosphere, becomes denser, and sinks. This sinking occurs in a few key locations, and the Denmark Strait is one of the most important. The cold water that sinks here flows southward along the ocean floor, eventually reaching the Antarctic region, where it joins other deep currents circling the globe. This circulation is crucial for regulating Earth's climate. It transports heat from the equator toward the poles, moderating temperatures. It circulates nutrients and oxygen, supporting deep-sea ecosystems, and it plays a role in storing carbon dioxide, pulling CO2-rich surface water down into the deep where the carbon can remain sequestered for centuries. The Denmark Strait cataract was formed relatively recently in geological terms. The ridge that the water flows over was shaped by glaciers during the last ice age, which ended about 11,500 years ago. During the Ice Age, massive glaciers covered much of Greenland and Iceland, extending out onto the continental shelves. As these glaciers advanced and retreated, they carved deep channels and shaped the seafloor, creating the topography that now controls the flow of deep water through the strait. Since the ice retreated, the cataract has been flowing continuously, a constant feature of the North Atlantic circulation. But there are concerns that this might not remain constant forever. Climate change is warming the ocean. As the polar regions warm, as ice caps melt, the salinity of Arctic waters is decreasing because more fresh water from melting ice is mixing into the ocean. Fresher water is less dense, even if it's cold. If the salinity drops enough, the water may not be dense enough to sink. And if the water stops sinking, the cataract could slow or even stop. This would have profound implications for global climate. The thermohaline circulation could weaken or shift, changing weather patterns, affecting marine ecosystems, altering the distribution of nutrients in the ocean. Some climate models predict that this could happen within the next century if greenhouse gas emissions continue at current rates. The Denmark Strait Cataract, invisible and unnoticed by most of humanity, could be one of the first major casualties of a warming world. But for now, it flows. Every second, 5 million cubic meters of cold water pour over the ridge and descend into the depths. It's been flowing since before humans built civilizations, before we invented writing or agriculture or any of the technologies that define modern life. It's been flowing through ice ages and warm periods, through mass extinctions and the slow evolution of species. It's a constant in a world of change, a reminder that the ocean operates on timescales and spatial scales that dwarf human experience. And it's just one example of how water, even underwater, can fall, can cascade, can create phenomena that rival anything on land in their scale and power. The Denmark Strait is not a sandfall in the traditional sense, but it follows the same principles. Dense fluid flows through less dense fluid driven by gravity, creating a cascade. Whether the dense fluid is sediment-laden water in a turbidity current, or sand suspended in clear water off Mauritius, or cold salty water pouring over a ridge in the North Atlantic, the physics is the same. Density drives the flow, gravity pulls it downward, and the ocean, patient and powerful, slowly rearranges itself according to these fundamental laws. But sandfalls are not just about physics and geology. They're also about life. The ecosystems that exist around and within these cascading sands are unique, adapted to conditions that would seem hostile to most organisms. Constant disturbance, reduced visibility, the risk of being buried under moving sediment. And yet, life finds a way. It always does. In places where sand is constantly falling, where the seafloor is a shifting, unstable surface, certain species have evolved remarkable adaptations to not just survive but thrive. Consider the black corals that cling to the walls of the Cabo San Lucas sandfall. Corals in general prefer stable conditions. They build their skeletons slowly, layer by layer, polyp by polyp, forming reefs that can last for thousands of years. But black corals are different. They're deep water corals, found at depths where light is dim or absent entirely. They don't rely on photosynthetic algae like their shallow water cousins. Instead, they feed entirely by filtering plankton and organic particles from the water, and they've evolved to tolerate high levels of sedimentation. When sand settles on their polyps, they can produce mucus to shed it, using ciliary action to move the particles off their surfaces. They're essentially self-cleaning, constantly fighting against burial. Their presence on the walls of underwater sandfalls is a testament to this resilience. Other organisms have adapted in different ways. Certain species of fish are attracted to sandfalls and turbidity currents because these events stir up nutrients and organic matter from the seafloor. The turbulence brings food into the water column where it can be more easily caught. So you'll find schools of fish hovering near sandfalls, feeding on the bonanza of suspended particles. Some fish have specialized gill rakers, comb-like structures in their gills that filter out edible particles from the water while allowing sand and silt to pass through. It's a delicate balance, feeding in turbid water without clogging their respiratory systems. Invertebrates, too, show remarkable adaptations. Certain species of sea cucumbers, echinoderms that crawl along the seafloor feeding on detritus, can burrow into sand to avoid being swept away by currents. When a turbidity current passes over them, they simply dig down, anchoring themselves in the sediment until the disturbance passes. Then they emerge and continue feeding on the organic-rich layer that the current has deposited. It's a strategy that requires being able to tolerate temporary burial to survive without oxygen for short periods, and to quickly relocate the surface once conditions stabilize. Microorganisms, bacteria and archaea that live in the sediment itself are perhaps the most abundant and least understood life forms in sandfall environments. These microscopic organisms mediate chemical reactions in the sediment, breaking down organic matter, cycling nutrients, releasing gases like methane and hydrogen sulfide. When a turbidity current deposits a thick layer of sediment, it buries the existing microbial community under meters of new material. You might think this would kill them, but studies have shown that microbial life can persist deep in sediments, even at depths of hundreds of meters below the seafloor. They're incredibly resilient, able to enter dormant states for years or decades, waiting for conditions to improve. When new organic matter is buried with them, when there's still a source of energy and nutrients, they can remain active, slowly consuming whatever resources are available. In this way, the microbial communities buried by turbidity currents become archives of life, preserved in the sediment layers, their DNA a record of what the ocean was like at the time they were buried. The ecosystems around sandfalls are also important for larger predators. Sharks, rays, and marine mammals often patrol areas where turbidity is high because they've learned that prey congregates there. The reduced visibility might seem like a disadvantage for visual predators, but many predators have other senses. Sharks can detect electrical fields generated by the muscle contractions of prey. They can sense vibrations in the water through their lateral line systems. Some even use smell, following chemical trails in the water to locate food. In turbid conditions, these non-visual senses become even more important, and predators that rely on them have an advantage over purely visual hunters. This creates a unique predator-prey dynamic in sandfall regions, where the constant disturbance of the environment has selected for animals with diverse sensory capabilities. But perhaps the most fascinating aspect of life around sandfalls is the role these systems play in transporting organic matter from shallow to deep waters. The ocean's food web is often described as a pyramid, phytoplankton. At the base, primary producers that use sunlight to convert carbon dioxide into organic matter. Zooplankton feed on phytoplankton, small fish feed on zooplankton, larger fish feed on small fish, and so on up the chain. But most of this activity occurs in the sunlit surface layers of the ocean, the photic zone, where photosynthesis is possible. Below a few hundred meters, sunlight fades to nothing, and without photosynthesis there's no primary production. The deep ocean relies on food that sinks from above, the constant rain of organic particles called marine snow. This includes dead plankton, fecal pellets from zooplankton, fragments of larger organisms, anything that's denser than water and slowly settling. But marine snow sinks slowly, and much of it is consumed or decomposed before it reaches great depths. This means the deep ocean is generally food poor, a vast desert with only sparse oases of life. Sandfalls and turbidity currents change this equation. When a turbidity current is triggered, especially one near the coast or near a river delta, it can pick up enormous amounts of organic matter, leaves and wood from terrestrial plants, soil rich in organic carbon, dead organisms from the shelf. All of this material, which would normally decompose slowly or be consumed in shallow water, is suddenly transported to the deep in a matter of hours or days. It's like a conveyor belt on fast forward, delivering a feast to the deep sea communities that normally subsist on scraps. Studies of the seafloor after major turbidity currents have shown temporary explosions in deep sea populations. Scavengers like hagfish, amphipods, and crabs appear in large numbers, feeding on the deposited organic matter. These feeding frenzies can last for weeks or months until the food is exhausted, at which point the populations crash back to background levels. But the impact lingers. The nutrients released by decomposition enrich the sediment, supporting microbial communities that in turn support higher levels of the food web. In this way, sandfalls and turbidity currents are crucial links between shallow and deep ecosystems, ensuring that the vast majority of the ocean, which lies beyond the reach of sunlight, still receives the energy it needs to support life. This connection between shallow and deep, between continents and abyssal plains, has been operating for as long as there have been oceans. Long before humans, long before mammals or dinosaurs or even fish, turbidity currents were transporting sediment from ancient continents into ancient seas. The geological record is full of evidence. Rocks called turbidites, formed from the deposits of ancient turbidity currents, can be found on every continent, often in places that are now far from the sea, lifted up by tectonic forces and exposed by erosion. Geologists study these turbidites to reconstruct ancient ocean basins, to understand how continents have moved, how mountains have risen, how the Earth's surface has been constantly reshaped by the twin forces of erosion and deposition. Every turbidite layer tells a a storm that raged millions of years ago, dumping rain on mountains that have since eroded to hills. A river that carried the sediment to the sea, where it settled on a delta. An earthquake that shook the delta, triggering a turbidity current that raced across a seafloor now uplifted and dry. The sediment settled, was buried by more sediment, was compressed and cemented into rock, was uplifted, was exposed, and now stands as a cliff face or a mountainside where a geologist can examine it, measure it, date it, and piece together what happened. Some of the most famous turbidites come from the Apennines in Italy, from the Pyrenees in Spain and France, from the mountains of California and Oregon. These rocks, now high and dry, were once at the bottom of the ocean, accumulating layer by layer as turbidity currents swept over them. The famous boomer sequence, a characteristic pattern of sedimentary structures found in many turbidites, was first described in rocks from the Apennines. It shows a progression from coarse sand at the base to fine mud at the top, reflecting the gradual settling of particles as the turbidity current slowed and deposited its load. This sequence is now used worldwide as a diagnostic feature to identify turbidites in the geological record. It's a signature, proof that a turbidity current passed through, and it's been found in rocks dating back hundreds of millions of years. The process that created it, the sandfall, the underwater avalanche, the slow cascade of sediment, is not a modern phenomenon. It's ancient. It's fundamental to how the Earth works, to how continents are eroded and ocean basins are filled, to how the surface of our planet is constantly recycled and renewed. In recent decades, human activity has begun to influence these natural processes in ways both subtle and profound. Dams built on rivers trap sediment, preventing it from reaching the ocean. This reduces the amount of material available to feed submarine fans and turbidity currents. Some major fans are now sediment-starved, receiving far less material than they did before dams were built. The Bengal fan, fed by the Ganges and Brahmaputra, still receives enormous amounts of sediment because those rivers drain such a vast area, but other fans have seen significant reductions. The Nile Delta and its associated submarine fan, for example, receive only a fraction of the sediment they once did because of dams like the Aswan High Dam in Egypt. This has implications not just for the deep ocean but for coastal areas as well. Beaches that were once replenished by sediment from rivers are now eroding because the supply has been cut off. Deltas are sinking because the sediment that once balanced subsidence is no longer arriving. The natural balance has been disrupted. On the other hand, certain human activities increase sediment delivery to the ocean. Deforestation and agriculture can accelerate erosion, sending more soil into rivers and ultimately to the sea. Mining operations, especially those involving tailings dumps into rivers, can release massive amounts of sediment, and climate change itself is altering precipitation patterns, leading to more intense storms that cause more erosion. The effects are complex and vary by region, but it's clear that humans are now a significant factor in the global sediment cycle, influencing how much material moves from land to sea, where it goes, and how fast it travels. We're also becoming more aware of how vulnerable our undersea infrastructure is to natural sand-moving processes. The telecommunications cables that were broken by turbidity currents in 1929 and 2020 are just examples of a broader vulnerability. There are hundreds of thousands of kilometers of cable on the ocean floor, connecting continents, islands, and even offshore oil platforms. These cables are relatively fragile. They're designed to lie on the seafloor undisturbed, but they can be damaged by many things. Fishing trawlers that drag heavy gear across the bottom, ship anchors, seismic activity, and turbidity currents. Each time a cable breaks, it must be repaired. A process that involves sending a specialized ship to the location, using remotely operated vehicles to locate the break, cutting out the damaged section, splicing in a new piece of cable, and burying it if possible to protect it from future damage. This can take weeks and cost millions of dollars, and if multiple cables are damaged simultaneously, as happened in the Congo turbidity event, the repairs can take months. During that time, communication between regions can be severely impacted. Internet speeds slow, financial transactions are delayed. People are reminded that the modern world's connectivity depends on physical infrastructure lying vulnerable on the ocean floor. The future of sandfalls and turbidity currents is uncertain. Climate change is expected to increase storm intensity and frequency in many regions, which could lead to more frequent turbidity events. Melting ice caps and glaciers will release enormous volumes of water and sediment into the ocean, potentially triggering large-scale sediment flows. Sea level rise will change the position of shorelines and the geometry of continental shelves, altering where and how sediment is deposited and where it might become unstable. At the same time, warming ocean temperatures could affect the Denmark Strait Cataract and other deep-water cascades driven by temperature and salinity gradients. If the formation of dense water in the polar regions slows or stops, the great underwater waterfalls that help drive the global ocean circulation could weaken. This would have cascading effects on climate, on marine ecosystems, on weather patterns around the world. The ocean is a connected system, and changes in one part, even changes deep beneath the surface where few people will ever see them, can ripple outward to affect the entire planet. But for now, tonight as you drift towards sleep, the sandfalls are still falling. In Mauritius, currents sweep sand over the edge of the submarine plateau, creating that mesmerizing illusion of a waterfall beneath tropical waters. In Cabo San Lucas, streams of sediment cascade over black coral-encrusted walls, falling past curious fish and ancient invertebrates into the depths. In the Denmark Strait, cold water pours over an underwater ridge, an invisible giant moving more water than all the world's rivers combined. And in submarine canyons around the world, sediment slowly accumulates, waiting for the next storm, the next earthquake, the next trigger that will set it in motion, sending it racing down into the abyss in a turbidity current that will reshape a small piece of the ocean floor and add another layer to the geological record. These processes have been happening for as long as there have been oceans, long before the first fish swam, before the first coral polyp built a reef, before life itself crawled out of the sea onto land. Sediment was falling through water, carving canyons, building fans, connecting continents to ocean basins. It's one of the fundamental processes of the Earth, as important as rain or wind or the movement of tectonic plates. And it's beautiful, slow and patient and inexorable, like everything in the ocean, operating on timescales that make human lifespans seem like heartbeats. You are part of this world. The atoms in your body were once part of mountains, eroded grain by grain, carried by rivers to the sea, swept by currents, perhaps even cascaded down an underwater cliff in some ancient turbidity current before being recycled through the biosphere and eventually becoming part of you. The ocean connects everything. It's not separate from the land or the atmosphere or life itself. It's all one system, constantly exchanging matter and energy, constantly in motion, constantly creating and destroying and reshaping itself according to laws older than memory. And somewhere in all of this, in the slow fall of sand through water, in the invisible cascades of cold water over underwater ridges, in the turbidity currents that race across the abyssal plains, there is a kind of peace. Not the peace of stillness, but the peace of processes so vast and so patient that they remind us of our place in the world. We are small. Our concerns are temporary. But we are part of something immense, something that has been unfolding for billions of years and will continue long after we are gone. Tonight, let the image of falling sand comfort you. Picture those grains spiraling slowly through blue water, catching the light as they descend, settling gently on the seafloor to join countless others. Each grain, a tiny piece of earth, completing a journey that began on a mountain somewhere, sometime. And that will continue when the sediment is compressed into rock, when the rock is uplifted by tectonic forces, when it's exposed to air and weather and begins to erode once more, starting the cycle again. The ocean's sandfalls are part of this eternal cycle, this breathing of the earth, this slow exchange between sea and land that has no beginning and no end, only continuation, only change, only the patient rearrangement of atoms across the face of a blue planet spinning in the darkness of space. Rest now. Let the sand fall. Let the currents flow. Let the ocean do what it has always done, what it will always do, slowly and steadily reshaping the world while you dream. If you've made it this far, if you're still awake, thank you for joining me on this journey into the deep. I hope you've learned something, felt something, been transported somewhere unexpected. The ocean holds so many secrets, so many wonders, and I'm grateful to share them with you. If you enjoyed this episode, consider subscribing so you don't miss the next exploration, and let me know in the comments where you're listening from, what drew you to this topic, or what ocean mystery you'd like to hear about next. Until then, sleep well, dream softly. and know that somewhere out there, beneath the waves, in the cold darkness, where light never reaches, sand is falling, slow and silent, writing the story of our planet, one grain at a time. Good night.